Hey guys, welcome back to Pop 'em Up Chem. We're continuing our path of focusing in on different functional groups as we go. Last time we did alkanes, combustion and free radical substitution. Today we're doing alkenes and electrophilic addition. Let's crack on with it. So we're going to look at what alkenes are, what makes them so reactive, and the main reaction that we focus on in IB, and hopefully that will also help inform our understanding of the stability of benzene. But for now, question to get started on, pause the video and have a go. Hopefully you remembered that you had a free radical substitution reaction, so you had 3 steps: initiation, propagation, and termination. Firstly, we want to quickly cover how alkenes are made. So the way they are made is by a process called cracking. In this process, we heat alkanes up and pass them over a catalyst that enables them to be broken down into 3 products: hydrogen, smaller alkanes, and alkenes. And both of these processes use heat. The exact alkene we're going to form varies depending on the conditions and the alkane we started with. So there's no correct way to write an individual cracking reaction, rather there's more possibilities. So if we look here at the breakdown of pentane, the pentane can go into ethene, propane and hydrogen, but equally we could have a situation where we got propene, ethane and hydrogen. Indeed, the longer the carbon chain, the more possibilities for outcomes there are. So in order to understand why alkenes are reactive, we need to think about sigma, pi and double bonds. So just a quick recap on that. You'll remember that our sigma bonds are the hybridized orbitals that exist on the interatomic axis along it, and our pi bonds are formed from the unhybridized p orbitals above and below the plane. And it's these pi orbitals that are away from the controls of the nucleus that make alkenes so reactive, because these electrons are able to easily move, and because they're able to easily move, they're able to participate in reactions more readily because they're available. So, in summary then, the reason that alkenes are more reactive than alkanes and they are a major industrial feedstock is because of this double bond, which allows them mobile electrons and makes them very attractive to electrophiles, as well as being able to polarize incoming molecules that come near it. So what exactly is an electrophile? Well, put simply, electro means negative from electron and phile means love. So it's something that loves electrons, or correctly, a species that is attracted to negative charge. So what does being attacked by so-called electrophiles actually look like? Well, we've got to remember our rules. And if we have here an electrophile in hydrogen bromide, it's got a polar bond, so it's got a partial positive and a partial negative charge, and we have the double bond, which is obviously going to be attracted to this partial charge. Remember our rules: no movement from positive charge. Although it says an attack by electrophile, it's a common mistake to draw the arrow from the positive to the electrons. We're always demonstrating the movement of electrons to positive or electron sinks, so we're going from the double bond to the positive charge. And it's this process that allows for addition reactions to occur. Now, all an addition reaction is you can think of it as opening the double bond and allowing each carbon that's currently sp2 hybridized to become sp3 hybridized and bond to 4 different groups by removing the double bond. The problem can be where if we call these A and B and carbon 1 and 2, how do we know whether A will go to carbon 1 or carbon 2, and the same with B? Luckily, there's a really simple rule to remember this. It's called Markovnikov's rule. the hardest bit about this rule is remembering the name. And this rule states that when any compound, HX, that's the electrophile, is added to an unsymmetrical alkene, the hydrogen becomes attached to the carbon with the most hydrogens attached to it already. So let's have a look at this example where we can draw the products of this in two ways. We can draw the Cl bonding to the left-hand carbon first, and in the second instance, the Cl bonding to the second carbon and the hydrogens switching around. Now, according to the rule, which one of these is correct? Well, looking at the alkene, we can see that it is indeed unsymmetrical, and we've got a HX. Now, the hydrogen becomes attached to the carbon with the most hydrogens, which in both cases is this hydrogen B on the right-hand side. So in our products, if we label them A or B, the hydrogen that we're adding from the HCl should have gone to carbon B because that already had the most hydrogens. So indeed, it looks like this top one is the major product. That will be produced the most because it will follow Markovnikov's rule. Now, I'm going to go through why this will work. However, this is the rule that you need to remember when you're drawing products, is always adding the hydrogen of that electrophile to the carbon that has more hydrogens connected to it. So let's dig a little deeper and see why this is. So the driving factor behind this is the inductive effect, or in this case the positive inductive effect. And we have to stop halfway through the reaction to see why this will occur. So we can see that we're going to form a bond between our carbon and our hydrogen, and our chlorine is going to take some electrons away from its bond, and that's going to leave us with two options. The hydrogen can go on this carbon on the left hand side and leave a positive charge ready for the chlorine to attack. And this is called a carbocation. And we can have the inverse. So we can have the hydrogen attaching to the carbon on the right, leaving the carbocation on the left carbon. Now, if we think back to our terminology, we have a primary and we have a secondary carbocation. Now, what the positive inductive effect tells us is that the electrons from the rest of the molecule, when there's a positive charge, they start shifting towards that positive charge, and they try to neutralize that charge and stabilize it. So the more electron donating groups we have next to a carbocation intermediate, the more stable it will be. The more stable it will be, the longer it can stay around, and the longer it can stay around, the more time this chlorine has to attack that carbocation and form the product. So because the primary is very unstable and the secondary is more stable, we do not tend to get the primary carbocation and therefore the product of the primary. Instead, we get the product of if the chlorine attacked this one to the top right, forming this product, which is going to be our major product. So we do not actually make this primary carbocation, and therefore, because we don't make that intermediate, we don't make the corresponding product. And we can use that to explain that primary will occur less than secondary, which will occur less than tertiary. And that's something you have to bear in mind when you are answering questions on this. But I know what you're thinking, how do I even get to drawing a mechanism? So although we're still going to be following the same rules that I introduced with the alkanes lesson, I'm also going to be giving you specific advice for looking at electrophilic addition mechanisms. So there are four basic rules or four basic stages to this reaction. First of all, the electrophile is attracted to the double bond. It then accepts an electron pair from the double bond, and when this happens, the carbocation intermediate is formed, and lastly, the negatively charged ion that's left from the electrophile reacts with the carbocation to form our final product. So let's draw out an example here. I'm going to draw out propene, and we're going to have the electrophile as hydrogen chloride, which we know has the polar bond. The double bond is going to attack the hydrogen and form a bond to one of the carbons, and the electrons from the bond between the carbon and the chlorine is going to move onto the chlorine atom. Two-sided arrows here, both these are electron pair movements. So where does that leave us? Well, we just have to follow Markovnikov's rule and know that the hydrogen is going to have attached to the carbon with more hydrogens, which is the one on the right hand side, and leave that carbocation intermediate formed. So that's our step 3 done. And then lastly, the negatively charged ion that is left over, that's the Cl-, is going to attack this positively charged center, and that is going to leave us with our product, which is going to have the Cl on the second carbon and the hydrogen on the last. It's important to bear in mind here we're looking at a generalized mechanism, so this will help you with the reactions of all the different alkenes. The chain length is just going to be a component of the question. You need to remember that your fundamentals of Markovnikov's rule, the positive inductive effect. Let's have a look at the reactions that you need to know and the mechanisms for a few of them. So the first one is what we've been looking at quite a lot, which is the addition of a hydrogen halide to an alkene. So here, when it's an asymmetrical alkene, we're going to have attacking the partially positive on the hydrogen, which is going to cause an intermediate carbocation to be formed on the carbon that is attached to the most other carbons, which will then be subsequently attacked by the newly negative bromine, or halide if it's another halide. And this requires no special conditions. If you're lucky enough to get a symmetrical halogen, a double halogen, then you don't even have to worry about Markovnikov's rule, because they will add equally over the double bond. That's due to the temporary induced dipole the double bond causes the molecule to have. Remember, one of the features of the electrons is that as the electrons draw closer, they induce a temporary dipole. Now, you don't have to worry about Markovnikovs for this, but you do have to remember that if we use bromine, Br2, that is the test or qualitative test for alkenes. If we go from brown to colorless, then the bromine has been added over the double bond, and we can test for the presence of alkenes. Again, this reaction recurs readily, no special conditions. However, for this one, which is the reaction of an alkene and water, you do have to remember the conditions. The water must be in steam, so in gaseous form, and we must use a phosphoric or sulfuric acid catalyst. So in this situation, we have the delta positive hydrogens on the water and the delta negative oxygen, and one of the hydrogens will be attacked by the electrophile of the double bond, just as we've mentioned before, which will split the water and leave a negative OH group to attack the intermediate carbocation. And for our last one, the mechanism would be slightly different, but you do have to remember that you have a nickel catalyst, and this is for hydrogenation, and this is simply making an alkene into an alkane by adding hydrogen equally over each side of the double bond. And now I can feel it. You're itching for some questions. So let's have a little look at some then. First question, draw the product of the reaction with propene and water. Pause the video. Pop them up! So let's just draw the mechanism out so you can get your thinking straight on this. So our intermediate is of course going to have a carbocation on the central carbon where there's two carbons attached, and then we're going to have the OH group attached in the middle. And just to clear that up, it's in there because the central carbon can have more positive inductive effect from the two groups on the outside. And that's why we get Markovnikov addition of the hydrogen going onto the carbon with the most hydrogens already attached. Try your hand at this one then. Draw the product of the reaction with butene and HBr. pause the video. Pop them up! Okay, so if you're reacting with HBr, then you know your double bond is going to open onto that hydrogen. Now, this is actually a symmetrical alkene, so if you ever got lucky enough with one of these in an exam, it doesn't actually matter which carbon you put it on because both of them are secondary, so the Br could attach to either, and in fact it's the same isomer to bromobutane, whichever one it lands on. But I hear some of you saying, what if the alkene itself, another alkene molecule that is, wanted to try and bond with that carbocation? Interesting question. Well, that actually leads us to our next topic, which is polymerization. Indeed, if we get the right conditions, usually high temperature and a catalyst like oxygen, but depending on the polymer, we can get the carbon-carbon double bond from each alkene to almost attach to the molecule in front of it, forming a long infinite chain. This is called polymerization, and you can see a kind of diagram of the process here. Now, we don't have to look at the mechanism in any detail, but we can see that for n number of the monomers on the left, we will get a chain that is n number of monomers long on the right. One thing that can be asked of you is to draw a polymer from a set of monomers, or the inverse. So let's go through a little simplified technique for this. We're going to draw square brackets, and then you're always going to draw two carbon atoms linked with a single bond, and these two carbons represent the carbons either side of the double bond. You then draw bonds going outside of the square brackets, and then you just almost fold above and below the chain. So this group here is just below the chain, the CH3, and then we draw an N to represent that there could be an infinite number. And what we're really imagining here is almost imagining the double bond is folding out and grabbing onto the molecule in front of it, and this process going on and on and on, forming a very, very long infinite chain. Remember, you don't need the mechanism for this, and this indeed isn't a representation of the mechanism, it's just to try and help you understand what is occurring. Another itch, you say? Question time it is. Okay, have a go at drawing the polymer formed from pent-2ene. Pause the video. Pop them up. Once again, following those three simple rules. Square brackets, two carbons joined by a single bond, and single bonds going out of the brackets. I'm going to label these carbons so you can see where I'm putting these. So I've got a CH3 below and a hydrogen above. I'll just draw a little circle around it. Again, hydrogen above, and I've got a C2H5, which I'll put a square around there. Don't forget my little N to represent the repeating pattern. Okay, here's one that initially looks tough, but I want you to do the same thing, but just focus on this double bond. That double bond, not the benzene ring. Pause the video. Pop 'em up! So once again, square brackets. I'm going to label the carbons again just so you can see. So all of these are indeed hydrogen apart from the one benzene group, which I'm going to draw in like this, and don't forget my N. So we're always focusing just on that simple double bond. So I wanted lastly to revisit and build on something we looked on in Unit 4, which is the structure of benzene, and to further explain its stability. One of the main things we can look at is the enthalpy of the cyclohexene ring. Now, if this were the case that we had alternate single and double bonds, the difference between C6H12's enthalpy and C6H10's enthalpy should just be able to be multiplied by 3 in order to be able to get that of benzene. That is if we have an alternate single and double bond structure. However, we find a big discrepancy between the theoretical value of minus 360 kilojoules per mole, and we find that benzene is much more stable than we would expect it to be. And if we have a think about what we've just done about double bonds and the nature of double bonds, that makes a little sense, especially when we consider the idea of delocalization. Let's just have a think about all of these sp2 hybridized carbon atoms in benzene for a moment. When we think about the alternate single and double bond system, if we actually draw in the p orbitals that would be above and below the plane because we have sp2 hybridized, then we have a lobe above and a lobe below. Now we could say that the double bond exists in between one carbon and another carbon. However, it doesn't seem, when we look at this, meaningful to say that we know where the double bond would be. And in fact, that's why we get a resonance form when we draw benzene, because it's equivalent to say that the double bond is here or on the carbon next to it. It doesn't make any difference. So we can draw those resonance, which is always equal to the one where the double bonds are on the alternate carbons. Now, the truth of the matter is, if that was the case, then we would see this theoretical value, and we would also see other bond lengths as well. However, what instead happens is, above and below the plane, the electrons combine to form a delocalized ring system, and this is very stable. There's the delocalization energy associated with delocalization, and this allows the enthalpy to be more stable than expected. Okay, hopefully that helps integrate that more. We will look at that further in HL when we look at reactions of benzene as well. So what next? Well, there'll be a video coming up about the extraction of limonene I'll be doing, which is a very common organic chemical that is present in citrus fruits, the structure of which I'm just drawing right now. There will also be questions on that from your practical workbook, and there are worksheets on electrophilic addition in the folder on Teams. Thanks again for joining me, guys. Remember to like, subscribe, share the video, and as always, practice makes slightly better.